We have gone through ionic compound nomenclature. Nomenclature means system of naming. So we've learned how to name ionic compounds. Now we're going to look at molecular compounds. Now it becomes more important that we be able to identify what kind of a compound are we looking at, because we have to use a different set of rules. So molecular compounds contain two nonmetals. Nonmetals don't form ionic bonds with each other because they all form negative ions. To have an ionic compound, you have to have You have to have a positive ion and a negative ion. Two negatives are not going to stick together. So the nonmetals, when they're together with each other, do not form ionic compounds. They form bonds and compounds by sharing electrons instead of transferring electrons. We cannot look at the periodic table like we do with the ions and just figure out how nitrogen and oxygen are going to combine with each other. And many of these combinations of elements, I'll save that one, combinations of elements can form more than one compound. We've talked about carbon monoxide and carbon dioxide, two compounds from the same two elements. Well, how do we know what their formulas are from their name or from their formula? So another example is nitrogen and oxygen. 1, 2, 3, 4, 5, 6 different compounds between nitrogen and oxygen. So there's lots of different combinations possible. When you have sodium and chloride in combination, there's one possibility. If you have one of those elements that needs a Roman numeral like iron, you have iron and chlorine. Iron forms a +2 and a +3 ion. There's only two compounds possible. When you get two nonmetals together, you've got a lot more possibilities. So what we do in the names is we use numerical prefixes. These are the same prefixes that we used for the hydrates. A couple of people asked, what happened to 9 and 10 on that other list? They didn't fit on the slide very well, so I left them off. Here they are. Nona is 9, and deca means 10. So we use these prefixes to specify how many atoms of each element are present in the molecular compound. We also then have to decide which element to name first and which to name second. Ionic compounds, it was always the metal first, the cation, and then the anion. Well, what do we do when we have two nonmetals? We pick the one that's most like a metal. Usually that'll be the element with the smallest group number. This concept here is not going to be huge. I'm not going to trick you with this on an exam, but students sometimes want to know, why does carbon come first in carbon monoxide? Why not oxygen first? Because carbon is closer to being a metal than oxygen, and so we've used that as a criteria to put carbon first. We want to have one correct name for everything so that there's not so much confusion. So this is the general form of the molecular compound names. We are only going to learn how to name binary molecular compounds, two nonmetals, okay? So we have a prefix in the name of the first element, and I think of the first element as kind of pretending to be a metal, so that element doesn't change the ending of her name. She just keeps her name. And then we have a prefix to indicate how many, and then we have the name of the second element, and just like in an ionic compound, we're going to change the ending to "-ide". So it's kind of following the pattern of ionic compounds, but there's no metal involved. To continue this bias against the number 1 that chemists seem to have, if there's only one atom of the first element, we usually leave the mono off. Mono means 1. We don't like the number 1, so we leave it off whenever possible. So this compound, NO2, there's only one of the first element. We're going to leave the prefix mono off. Otherwise, we end up with a lot of compounds starting with mono, and when you go look them up in the index, there's just way too many M's. So just nitrogen for that. Here's that, nitrogen. And then we look at the second element is oxygen, so that becomes oxide, and we use the prefix to say there's two of them. So this becomes nitrogen dioxide. Students generally like naming molecular compounds, and then they try to use this for all the other types of compounds too. So restrain yourselves. There are two compounds you need to know about that are kind of special. H2O and NH3. These do have systematic names, but they always go by their nickname, their common name. What do we call H2O? Water. And NH3 is always called ammonia. We could give them names like this. We could call this dihydrogen monoxide. And, you know, if you have alarmist friends or parents, you can go home and you can say, I was exposed to dihydrogen monoxide in chemistry class today. I think I might die. Maybe you could get some sympathy or ice cream for dessert or something. Yeah, you were exposed to water. You washed your hands or you had a drink, right? Big deal. You wouldn't want to be exposed to ammonia. It smells really, really bad. But we could call this nitrogen trihydride, but we don't. It's just such a common compound that everybody calls it by its nickname, ammonia. So let's name this compound N2O5. So let's practice identifying what kind of compound. So the first element is nitrogen. Is it a metal? No. We've got two nonmetals. We can use the prefixes. So the first element is nitrogen, and there's two of them, right? So we're going to write dinitrogen. And then the second element is oxygen. She'll change the ending of her name to oxide. And how many oxygens are there? 5. What's the prefix for 5? Penta. So we might write pentaoxide. Now this is where things get a little bit muddy. You see this double vowel here? Sometimes, but not all the time, we drop the ending vowel of the prefix. So you might see this as pentoxide. There seems to be not a very consistent pattern for dropping the vowel or not. And so I'm going to accept either as correct. If I was asking you to write this formula and you wrote pentaoxide, or if you wrote pentoxide, I would count either of them correct. But I want to tell you about that because if you see pentoxide instead of pentaoxide, you might say, well, what's going on there? Well, the writer decided to drop the vowel because it looks kind of funny sometimes. Like with carbon monoxide, that's not an R. Carbon, it probably should be monoxide, right? Don't tell me that doesn't look weird. It looks like monoxide, right? So we drop the O there. But sometimes we don't drop the vowel. So we're just going to not worry about it. So any questions about naming the compound? Let's write a formula. So here we have a formula, phosphorus tribromide. We can recognize this as a molecular compound because the first element is a nonmetal, and the second element is a nonmetal. And then this prefix in there is a big clue as well. So what's the symbol for phosphorus? P. And how many phosphorus atoms are in this formula? Just one. We left off the mono. Tribromide. Bromide is Br, and how many bromides are there? 3. So PBr3. Any questions? This one tends to be easier for students, especially after we've done the ionic, which tends to be confusing. Then you're like, oh, this is so much nicer. Yeah, so that's all we're going to do with that. You will be expected to name and write formulas. Another category of compounds are acids. There are several different definitions of acids. The one we're going to use for now is that acids are molecular compounds that release hydrogen ions when dissolved in water. So for nomenclature purposes, we can recognize acids because the formulas start with H. Okay? Hydrogen, although he likes to hang out with lithium, is a nonmetal. And we've got hydrogen and other nonmetals. This is a molecular compound. But we name most of the acids slightly different than we do the molecular compounds. So HCl, how would we name that as a molecular compound? Hydrogen monochloride, right? Well, that's a molecular compound. It's a gas in its pure state. You don't need to remember that. But if we dissolve it in water, it forms hydrogen ions and chloride ions. It's not an ionic compound, but when you put it in water, it forms ions. When it's dissolved in water, we name it as an acid. And this symbol, AQ in parentheses, stands for the word aqueous, which means dissolved in water. So, acids are ionic compounds. Acids are molecular compounds that when you dissolve them in water, they form hydrogen ions. They're technically only considered an acid if they're dissolved in water. Characteristics of acids. They have a sour taste. Sour Patch Kids, you put them in your mouth and you pucker up because it's really sour. Personally, I don't understand why people do that to themselves, but some people seem to like them. They are sour because there's an acid on the outside. That powdery white stuff has malic acid in it, which just is an acid from grapes. It's not going to kill you or anything. Acids do dissolve many metals. They'll dissolve iron and zinc and magnesium, but they don't dissolve some of the others like silver, gold, and platinum. And their formulas generally start with H. So here's a couple of examples, HCl and H2SO4. We recognize these as acids or potential acids because the formula starts with H. There's two kinds of acids, binary acids and oxyacids. I prefer to think of them as oxyacids and the other kinds. Oxyacids, as the name implies, contain oxygen. It's an acid that contains oxygen in its formula. The binary acids are usually hydrogen and one other nonmetal, but there are a couple of exceptions, and that's why I'm not a big fan of the name binary acid. So we have two different sets of naming rules, one for the binary acids and one for the oxyacids. So let's look at naming those binary acids first. The pattern here is that we put the prefix hydro at the beginning of the name. The middle of the name is the element name, but we're going to change the ending, not to "ide," but to "ic." And then we're going to throw the word acid on at the end. So hydro something changed to "ic," acid. So let's look at this. Here we have HF aqueous. HF, two nonmetals, it's dissolved in water, starts with a hydrogen. So we're going to name this as an acid. Is there any oxygen in the formula? No. So we're going to use that hydroblankic acid pattern. So starts with hydro. And fluorine is the name of the other element. So fluor, try it again, fluor, not "ide," but fluoric, and then the word acid. Hydrofluoric acid. The nice thing about acid names is they all have the word acid at the end, so it's really easy to tell that they're acids because it just says so right there in black and white. Let's do another example. This is the one that makes me not like the term binary acid. Starts with H. Oh, we better put it in water. Does it have an oxygen in it? No. We need to use the binary acid rules. Is it actually binary, though? There's 3 elements. When acids dissolve in water, they form hydrogen ions and an anion. They separate into just 2 pieces. So we're going to get hydrogen ion and what's the name of that? Cyanide. So we're going to apply the pattern hydroblank-ic acid, but we don't have one element. We're going to use this name. So then this is hydro. We're going to take cyanide and get rid of the "ide" ending and swap it for "ic." Hydrocyanic acid. Any questions? Let's do a different type of example. Let's take hydroselenic acid and write the formula for it. We recognize it as a binary acid because it starts with the prefix hydro. So there's hydrogen ion and something else. The other element is selenium. What charge does selenium take as an ion? 2 minus. We need one more hydrogen, yes. So the formula for this is going to be H2SE, and then we really should put AQ behind it, because it's an acid when it's dissolved in water. The charge on the anion that forms when it dissolves in water is what tells us how many hydrogen ions are needed. In HF, hydrofluoric acid, fluorine has a -1 charge when it becomes an ion, and so there's only 1 hydrogen. Same with hydrocyanic. Cyanide has a -1, and so there's only 1 H+, and so the formula is HCN. Naming the oxyacids. The oxyacids are named based on the name of the oxyanion that's present. So you look at the formula, you cover up the H's, and see what the other elements are. You figure out, well, what's the name of that oxyanion? And I also got some questions on the 1-minute paper about not understanding the names for the polyatomic ions. There's a limited amount of stuff to understand there. Most of it is because. Nitrate is NO3- because that's what everybody else on the planet decided to call it. And so we just have to go along with it. There's not really a lot of understanding. So what we're going to do is we're going to figure out what the name of the oxyanion that's in the acid is, and then we're going to mess around with the ending of the name again. If the ion name ends in "ate," we're going to change the ending to "ic." If the ion name ends in "ite," then we change the ending to "us." There's a lot of things in chemistry where we have 2 things on one side and 2 things on the other side, and we have to remember how they pair up. And so I've come up with tricks that help me remember that, because I'm not real big into just rote memorization. If there is no great reason, then I make up silly reasons, right? So here's a silly sentence that can help you remember that. I've heard others, but this one works for me. Rick ate him before he could bite us. How's that for being silly? It says nothing about what species of thing him is. You know, maybe it's a cow or a cougar or something, I don't know. Hopefully not another human being. Rick ate him before he could bite us. So how does that help? Bite us. We need to remember that "ite" and "us" go together, and that "ic" and "ate" go together. You could also think about tasting something. I ate it and said ick because it was nasty. Ick and ate go together. Okay? Very important. So let's name HNO2, aqueous. So we look at this, we see hydrogen at the beginning. We think, oh, this is probably an acid. We see aqueous, it's dissolved in water. Yeah, we're going to name this as an acid. Then we look for oxygen. If there's oxygen in the compound, then we need to name it as an oxyanion. So we're going to cover up the H. I covered it up with my arrow. What's left is NO2. So we need the name of NO2. Nitrite. So we change ite to what? Us. Ick and ate go together. Ite and us. Bite us, right? So we change nitrite. This becomes nitrous acid. Any questions? What about the H? Well, we're not really just leaving the H out, because the fact that it ends in acid tells us that there's hydrogen. Yeah. All acids, at least as far as we go in this class, are going to have an H at the beginning. How would we do this? Perchloric acid. We recognize this as an oxyacid because it does not start with hydro. Hydrocyanic, hydronitric, all of those other ones just are hydrogen and one element. Perchloric doesn't start with hydro. So we're going to take this perchloric and reverse the switch on the suffix. So perchloric is from perchlorate ion. Then we need to know what the formula for perchlorate ion is. Anybody remember? Cl, right? O4, and the charge is -1. The charge tells us how many hydrogens we need, because it's going to have hydrogen on it because it's an acid. And so we need the H plus and this guy to balance each other in terms of charge. There's +1 plus 1 minus 1, and so we put them together, and we've got HClO4, and we're going to put AQ at the end. And so that's the formula. Any questions? I assigned a worksheet. We're not going to be doing it in class, but I think it's going to be due a week from today. It's on Blackboard. The due date is on Blackboard and all of that. And it's nomenclature. It's practicing doing this sort of thing. After the test, you should go and start working on that. And if you have questions, then ask me, and I'll help you, okay? So we kind of did an example of all of this, writing formulas business already, but here's it spelled out. So if the name ends in acid, the formula is going to start with an H. You're going to write the formula as if it were ionic, even though we know it's molecular. It's molecular, but when we put it in water, it forms ions. The hydro prefix tells us it's a binary acid. If there's no prefix, then it's an oxyacid. If it doesn't say hydro at the beginning, it's got oxygen in it. For oxyacids, if it's an ic ending, like hydrochloric acid, that's not a good example. Chloric acid would be an oxyacid. Then we know that comes from chlorate. If it ends in us, like nitrous acid, that comes from nitrite. So let's write formulas for these acids. Oh, I already did the first one. Hydrocyanic. HCN. There's H plus, always H plus in an acid. And cyanic comes from cyanide. The charge being -1 tells us that we just need one hydrogen. It's HCN, aqueous. Phosphoric acid. Is this binary or oxyacid? Oxyacid. So the ic ending came from It's a phosphate or phosphite? 8. Phosphate. So we need the formula for phosphate, PO4, 3 negative. So how many hydrogens do we need? 3. So it's going to be H3PO4. And then A cubed. Hypochlorous acid. What kind of acid? Oxyacid. Hypo and hydro kind of look alike, right? But they're not the same. This is hypo. Hypochlorous comes from hypo what? Chlorite. Hypochlorite. What's the formula for the hypochlorite ion? ClO minus 1. So we need 1 H plus. This is HClO. Any questions? You've probably heard about acid rain. There are certain pollutants, such as these guys, nitrogen monoxide, nitrogen dioxide, sulfur dioxide, sulfur trioxide. These are formed, from combustion of fossil fuels and various things. They will form acids when they mix with water, and then that acid comes down in the rain. And here are some pictures demonstrating what happens. Not all tree deaths are due to acid rain, but acid rain does have a big impact on the health of trees in the forest. Here you see two statues, originally identical. This one has been subjected to more rainwater than this one, and you can see it's just being eaten away over the years. And so that's a good reason to cut down on pollution, because some of it forms acid in the clouds.